In this lesson, I'm going to teach you how to rationalize denominators of expressions with surds in them, and I'm going to explain why that's really important. Now, as the name implies, rationalizing the denominator involves rewriting a fraction so that the denominator of the fraction is a rational number. Now, the reason we want the denominator to be a rational number is because maths is much easier when you're dealing with a rational denominator. So that means that anytime we see a surd in the denominator, we have to find a way to turn it into a rational number, and that's going to force all the surds to end up in the numerator. So it really just comes down to convenience. Math is usually easier anytime you have surds in the numerators. Let me give you some examples of this. So to show you that surds in the numerator are much more convenient, I want you to simplify both of these fractions. You can pause now if you'd like to give it a try on your own. But in the first fraction, I've put the surds in the numerator, and in the second fraction, I've put the surds in the denominator. Now we're just going to use the standard technique that was shown in the simplifying fractions lesson, where we just multiply the bottom by the top, then this bottom by this top, and then we multiply the two bottoms together. When we do this to both of these examples, I think you'll see that the answer we get in the first case is going to be much nicer than the answer we get in the second case. But without further ado, let's go ahead and get started. In the first example, I'm going to multiply this 4 by this root 2, and then this 3 by this root 5, and then I'm going to multiply the 3 and 4 by each other. So therefore we can say that root 2 on 3 plus root 5 on 4 is the same thing as 4 root 2 plus 3 root 5 all over 3 times 4. Now of course 3 times 4 is just 12, so let's just multiply them. So once we've done this, we can see that we've combined two different fractions into a single fraction. Now let's try to do the exact same thing for the second case. Let's start by multiplying these and then multiplying the bottoms just as we did before. So in both this case and in this case at the bottom, we end up with a single fraction. But I want you to notice the main difference. The resulting fraction here actually has 4 different surds in it, but the fraction we had at the top only has 2 surds in it. Now, as you've already hopefully realized by now, less surds equals better, and more surds, that's generally a bad thing. The algebra for surds is much harder than the algebra for any other kind of number, and therefore it's really a benefit to have as few surds as possible in the final answer. So therefore, before we even start the second problem, we would try rationalizing both of the denominators in both of these fractions. If we do that, we'll actually end up with an easier problem to solve than the one we already have. Now, there are 2 different ways that we could put surds in the numerator, and it's going to depend on which case you have. So first, I want to talk about the simple case. Rather than showing you the simple case in general, how about I bring up an example and we work through it together? Now, the simple case refers to any situation where you have a single, standalone surd in the denominator. The simple case hinges around the fact that squares can be undone by square roots. So, for example, if you have the square root of a, all squared, then we can rewrite the square root of a as a to the power of 1/2. And then, by the index laws, we can say that 1/2 times 2 is going to be the same thing as 1. So that means the square root of a all squared is the same thing as a to the power of 1. But then, a to the power of 1 is the same thing as a, so we don't really need to write that power of 1 there. Now initially, this seems like a little bit of a detour, but it's really not. We want to convert this surd in the denominator into a rational number. So what we want to do is we want to somehow multiply it by the square root of 5 one more time. If we multiply by the square root of 5 in the denominator, we can go ahead and just square it, and that will get rid of the square root for us. But of course, that would also change the value of this whole thing, and we don't want to change the value. So the best thing we can do is we can just multiply by 1. As we know, multiplying any number by the number 1 does not change its value. Anything times 1 is itself. But one of the cool things about the number 1 is you can write it in lots and lots of different ways. For example, you could write the number 1 as 6 over 6, or you can write it as 10 over 10, Or maybe you can also write it as the square root of 5 over the square root of 5. Now, the square root of 5 over the square root of 5 is still the same thing as the number 1. These two would just cross out and you'd be back to the number 1. So therefore, by multiplying by the square root of 5 over the square root of 5, you have not changed this original value over here. But you actually have achieved something pretty useful. If you look carefully at the denominator, I want you to notice that you have the square root of 5 times the square root of 5. And that of course is the same thing as the square root of 5 squared. And of course, I also multiplied this 3 by the square root of 5. Because remember, when you're multiplying fractions, you multiply the tops and the bottoms. After this, we just use the fact that the square root of a squared is the same thing as a. And that means the square root of 5 squared must be the exact same thing as the number 5. So that immediately tells us that 3 over root 5 is the exact same thing as 3 root 5 all divided by 5. In the original, we had a surd in the denominator, but in this new version, we do not have a surd anymore. We have a rational denominator. So therefore, in the general case, if you have a situation where you have a surd in the denominator, you just want to multiply by 1 to get that surd out of the denominator. But instead of writing it as 1, we write it as the square root of a divided by the square root of a. After this, you just go ahead and multiply the tops and the bottoms. When you do this, this is going to leave you with the square root of a all squared on the denominator. After this, we use the fact that the square root of a all squared is the same thing as a, as we showed before. So therefore we can say that 1 on the square root of a must be the exact same thing as the square root of a all divided by a. But there is actually a more complicated case, and that case occurs when the number on the bottom is not just a surd. Sometimes it's possible to have a surd mixed with a rational number, and when that happens, you need to be a bit more careful. So, as we said in the lesson when we first introduced surds, surds are totally incompatible with rational numbers. So it is totally possible to have a denominator like 2 plus the square root of 3. Whenever that happens, you need to be a little bit more creative. So again, I think this is actually easier to see with an example. So let me give you one and we'll see what happens. So this time I'd like to rationalize 5 over 3 minus the square root of 2. Now my first inclination would just be to multiply by 1, where 1 is again 3 minus the square root of 2. Now if we just went ahead and did this, we'd end up with 3 minus the square root of 2 on the top and on the bottom, and that would lead to 3 minus the square root of 2 all squared. But in this side note down here, I said that we don't want 3 minus the square root of 2 all squared, and I'm going to try to show you why. I want you to remember that in order to simplify this, we have to expand it first. That's going to give us 3 squared and then the square root of 2 squared, but then we also have to multiply by 2 times 3 times the square root of 2. If we continue to simplify this one more time, I want you to realize that 3 squared is 9, and then the square root of 2 squared is the same thing as 2. Now after this, we can say that 9 plus 2 is the same thing as 11, and 2 times 3 is the same thing as 6. Now at this point, I hope you can see why we don't use this. By squaring 3 minus the square root of 2, you end up with 11 minus 6 times the square root of 2. Notice that you do not get rid of this square root of 2. So if we multiply by 3 minus the square root of 2, we would not be getting the surd out of the denominator. So instead, we need to come up with something a little bit more clever. We need to square this without somehow ending up with another square root of 2 on the other side. But the trick comes to us from a slightly unlikely place. I want you to recall the difference of 2 squares. The difference of 2 squares tells us that if we have a minus b times a plus b, that's going to be the same thing as a squared or minus b squared. Now initially that doesn't seem to be too useful, until you realize that you could think of this 3 as the a, and you could think of root 2 as the b. On the other side, we're going to square a and we're going to square b, but we don't have a b appearing on the right hand side, and that means we will not have a surd. Let me demonstrate. So, for example, if we had 3 minus the square root of 2, all times 3 plus the square root of 2, then by the difference of two squares, the result would be 3 squared minus the square root of 2 all squared. And we can also say that the square root of 2 all squared is, of course, the same thing as the number 2. Now, 3 squared is the same thing as 9, and then 9 minus 2 is the same thing as 7. So this whole thing just ends up being the number 7. So that actually seems like a pretty good game plan. Rather than multiplying by 3 minus the square root of 2, all over 3 minus the square root of 2, instead we'll multiply by 3 plus the square root of 2, over 3 plus the square root of 2. If you're interested in the terminology, we would say that 3 plus the square root of 2 is called the conjugate of 3 minus the square root of 2. Now, of course, the main reason we did this is because we have 3 minus the square root of 2 times 3 plus the square root of 2. And as we already know, that is the exact same thing as the number 7. So we might as well go ahead and replace it. But then after this, I want you to realize that we're multiplying this 5 on 7 by this 3 plus the square root of 2. So I'm going to put brackets around 3 plus the square root of 2. Now at this point, we're actually done. I want you to realize that 5 divided by 3 minus the square root of 2 is the exact same thing as 5/7 of 3 plus the square root of 2. So returning to the general case, anytime we have a situation where we have something like 2 plus the square root of 3, we need to look at the difference of two squares. So using the idea of a difference of two squares, if we have something like 1 over a plus the square root of b, we need to multiply by a minus the square root of b. If we want to use the difference of two squares on something like a plus the square root of b times a minus the square root of b, we're just going to end up squaring the first, so we'll get a squared. Then we're going to square the second, so we'll get the square root of b all squared, which as we know is the same thing as b. And then we just subtract one from the other. So therefore, we multiply by whichever bracket we are missing in our particular expression. In this expression, we already have a plus the square root of b, so we're going to multiply by a minus the square root of b. We call this the conjugate of the other term. Now, if we just use the fact that a plus the square root of b times a minus the square root of b equals a squared minus b, then we can go ahead and just multiply these to simplify it. And then this fraction on the left isn't really necessary anymore, because multiplying by 1 doesn't do anything. So therefore, we're forced to conclude that 1 over a plus the square root of b is the exact same thing as a minus the square root of b all over a squared minus b. Of course, the benefit of this one is that there are no surds in the denominator. So therefore, anytime you want to rationalize something like 5 on 3 minus the square root of 2, you just need to multiply by the conjugate on the top and the bottom, and then simplify. And that just about completes our example, so let's go ahead and summarize this lesson. In this lesson, we explained that maths is much easier anytime all of your surds are in the numerator. So anytime you have a surd in the denominator, we need techniques to actually rationalize them. After I showed you an example of why maths is actually easier with surds in the numerator, I started with the simple case, and that occurs anytime you have a surd on the denominator with no rational part. Now for the simple case, if we had something like 1 over the square root of a, you wanted to multiply by the number 1, which in this case was the square root of a divided by the square root of a. When we actually performed this multiplication, you ended up with the square root of a divided by a. So that means 1 over the square root of a is the same thing as the square root of a divided by a. The difference between the left and the right, however, is that the surds appear in the numerator on the right hand side, and that's exactly what we're after. However, because surds really don't like to mix with rational numbers, like this, you can have a situation where you have a rational number and a surd on the denominator. In order to simplify these, rather than multiplying the top and the bottom by the denominator, we instead multiply the top and the bottom by the conjugate of the denominator. Now, these two techniques will get you through most of the cases you will want to rationalize, but there are some harder ones out there. For example, what if you had something like 1 over the square root of 2 plus the square root of 3 plus the square root of 5? How would you rationalize something like that? I'll leave something like that as a challenge for you, but there are many other problems that you could come up with. But in general, these two will get you through 90% of the cases you want to solve. Now, at this point, you might not be totally appreciative of how much easier rationalizing actually makes your maths. But once you see a few examples, you'll more or less always rationalize things anytime you see something with a surd in the denominator. You'll definitely see this as we do more and more mathematics that involve surds. But at this point, I'd like to end this lesson on rationalizing the denominator. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.